All right, so we're looking at the 2022 Set 1 AP Physics C Electricity and Magnetism FRQs. There'll be a separate video for Set 2. And if there's any corrections, I'll put it in the description below or in a pinned comment. So here we have a non-conducting sphere of uniform volume charge density surrounded by a thin concentric conducting spherical shell as shown in the cutout view. The sphere has a charge of negative Q. So this guy has negative Q. And the outer shell has a charge of positive 3Q. The radii of the inner sphere and the spherical shell are r and 4r respectively from this picture. Determine the charge on the outer surface of the shell. So because there's a minus Q here, there's a positive Q here, okay? And then on the outer shell, there's a positive 2Q to balance that. Because that, or not balance it, but to make the net charge 3Q. Why is the charge Q positive and negative? Why do they match? Well, if you drew... You know the electric field in a conductor should be 0, so if you draw a Gaussian surface in that shell, it should contain 0 charge because the electric field is 0, so that's why it has to balance that. Anyway, so it's plus 2Q here. Using Gauss's law, derive an expression for the electric field at distance r from the center of the sphere for r less than r. Express your answer in terms of... So we're going to do a little shell here, all right, and it contains charge, so we're going to do the integral of the electric field over the area. And you're going to do a spherical Gaussian surface. That equals Q enclosed over epsilon naught. Now this part is easy. This is E times 4 pi r squared because it's just the electric field times the surface area. That's assuming that the electric field's uniform over that surface. The Q enclosed, you have to think about, you have to look at the ratio of the volumes times the total charge. So it's Q times the ratio of the volume enclosed over the total volume total. Right, because that's the proportion of the charge, because it's uniformly distributed. So this would be 4/3 pi r cubed over 4/3 pi big R cubed. And so the 4 pi's cancel. That's going to be r cubed over little r cubed times q. And then we are going to, let me just rewrite that. And then we're going to plug that in for the charge enclosed. So that is r cubed over big R cubed q, and then you can divide by 4 pi. You can divide by 4 pi and divide by r squared. R squared cancel with those, so you get electric field is r over 4 pi r cubed times q. The magnitude of the electric field at r is 8 newtons per coulomb. Calculate the value of the electric field at r equals 2r. I don't know why I wouldn't just do Gauss's law. I actually have no idea what this is telling me. Other than like you have that, I guess you're having that number. You don't know what Q is. So I think what they're saying is you're not going to put your answer in terms of Q in that case, like you did for these. This is going to be a numerical answer. So if I draw a Gaussian surface outside, I'm just enclosing the total charge Q, right? So you would say, using the same integral, is you would say that is E times 4 pi r squared equals Q enclosed, which is just Q over epsilon naught. So the electric field is just Q over 4 pi r squared epsilon naught. Now when r equals big R, what you should find is that this should be 8. So what you're saying is that when I plug in big R, the electric field is 8 equals Q over 4 pi r squared epsilon naught. And then the question is when r is equal to 2r, what is the electric field? It's Q over 4 pi 2r squared epsilon naught. So what's the relationship? I doubled the r, and so the electric field should drop by 1/4 because it's squared. Right? So the electric field should be 8 divided by 2 squared, which is 2 newtons per coulomb. You could have solved for Q and done all of that work, but this is sort of a ratio. I double the R here. How's the electric field going to change? Derive an expression for the absolute value of the potential difference between the outer surface of the sphere and the inner surface of the shell. Express your answers in terms of QR. So in terms of the potential difference, we're just going to do integral of E dr, right? And we're going to integrate from 0 to, well, let's look at our distances. We're going to go from this point here and integrate all the way to this point. So we're going to go from big R to 4R, right? Big R to 4R of the electric field, which we found over here, which was Q over 4 pi R squared epsilon naught, right? And what should I do? Should I find Q? Maybe it would be helpful to find Q. Let's say Q is equal, like from this expression here, Q is equal to 32 pi R squared epsilon naught. Okay, I'm just kind of being lazy about my calculator, so I don't really want to do that. So we'll just put our answer in terms of Q, but this is Q over 4 pi. What's the integral of epsilon naught? What's the integral of 1 over R squared is negative 1 over R from R to 4R. So this would be Q epsilon naught over 4 pi, negative 1 over 4 pi, plus or minus negative 1 over, not 4 pi, 4R, plus 1 over R. And we know that Q is equal to 32 pi squared. So this is 32 pi R squared epsilon naught over 4 pi times negative 1 over 4R plus, oh, actually they said in terms of Q, sorry. Q, R, and physical constants. So this would be fine. You could just leave it like that, or you could simplify that if you wanted to. That would be fine though. On the following axis include regions 1, 2, and 3. Sketch a graph of the electric field as a function of distance r from the center of the sphere. So let's look at our first expression. It's a linear relationship with r. So the electric field goes up as a function of r. So it's going to go up. Then it's going to decrease 1 over r squared, I believe, is what we got. The electric field is going to go 1 over r squared, so it's going to decrease. And then the electric field then pops up again. It's going to go to 0, and it pops up to another point because of the charge, and then it's going to decay 1 over r squared, so it's going to be like that. And this charge density is because, like, right there, boop, it's going to just jump because of that charge. Enclosed. I think that's right. Yeah. Yep. On the following axis includes region 1, 2, and 3. Sketch a graph of the electric potential. So electric potential is, you do the, let me see. You're going to do the E dot dr to find the potential. So what that means is, or another way to think of it is the derivative of the voltage is supposed to equal the electric field. So the slope is supposed to be the electric field. So it's going to be quadratic. It should go up. And then this is the slope. Or maybe I made it too narrow. Going to go up. And then the slope's going to be positive still. It's just going to be, oh, it's negative. Shoot. I think this whole time I'm messing up the charge because it's negative Q on the inside. All of this is supposed to be negative. Shoot. Negative Q. This is negative here. I think this part's still fine, but it's all of these should have been negative. Sorry, I messed that up. So if it's negative, that means the electric field. I was just noticing why they give me positive and negative. So the electric field, when I integrate that, actually the potential is going to go down. So I think they like it would go down linearly, then it would die off, then it's going to jump up, and then die off of 1 over squared like that. So that's what it's going to look like. So instead, what this thing is going to do is the slopes are negative, so it should be a quadratic downward. Then it'll like kind of get more and more negative. And then the potential, then it starts to increase at that point. So then it will 1 over r squared, so it'll be like 1 over r. So it'll be positive sloped, and then more yeah, it'll be more like this then. Yeah, something like that. Yeah. Okay, good. I think hopefully that makes sense. All right, second one. Plates of a certain variable capacitor of adjustable area. Experiment was performed to study the potential difference across the capacitor as it discharges through a resistor. Circuits to be constructed with the following available equipment. Single ideal battery of potential difference delta V0. A single voltmeter, a single resistor of resistance R, and a single uncharged variable capacitor set to capacitance C, and one or more switches needed. Use the symbols, draw a schematic diagram of a circuit that can charge a capacitor and may also be used to study the potential difference across the capacitor as it discharges through the resistor. So we just make where's a battery? This is pretty easy. We want to charge a capacitor. We'll put a switch here. We'll also put a resistor here. Oh, wait, you want to discharge the capacitor. So you want to close it. No. We want to charge the capacitor. And then we might want to, let's see. How do I want to make this? I want to make it so where I can close the switch and charge the capacitor. But then I might, at the same time, I might want to discharge it through another resistor like this. Oh, I have a single resistor. Oh, shoot. So then what I want to do is give me a second to think about it. You want to be able to discharge it but I need to use it to charge. So it's like the resistor always has to be in series with the capacitor because I have a single resistor. I can't do anything about that. But I can shunt it to ground, I guess, is the way you want to think about it. So it's like I'm going to have this switch, but it's going to be in one position or another, right? Like this is the switch here. Okay, so you're going to either go from there to there, basically. And then you want to measure the voltage as it discharges through the resistor. I'm going to just put a voltmeter in parallel with the capacitor like that. Okay, I think that's it. The capacitor is fully charged by the battery. At time t equals 0, the capacitor starts discharging through the resistor. So let's just make it this way. Like you make it like this, and then you'll disconnect it, and then you'll discharge it to ground. Show that the potential difference across the capacitor as a function of time is this as the capacitor discharges. Okay, so how do we do that? Well, we know, let's say this is R, this is C. We know when it's fully charged, we know the initial voltage on the capacitor is initially, so for t less than 0, or if t is approaching 0, like for the voltage at t equals 0 right before we open the switch, we know there's no current flowing through the capacitor. So that means the capacitor takes the full voltage of the battery. It's the what's the initial voltage? We'll just say it's the initial voltage. And then if you wait a long time, as the voltage goes to infinity, you know that this thing should discharge all the way to 0. And you know the time constant is RC. So you know the voltage should have this general equation. I don't know if they would want you to set up a differential equation. I don't think they would do that. So you know V of 0 is V0. So if you plug in 0, that's A plus B e to the 0. That's just A plus B is equal to V0. And then you say V at infinity is A plus B e to the negative infinity. That's about 0. That's A. And that's equal to 0. So that tells you between those two, B equals V0. So therefore, you know the voltage is just B0 is B, which is V0, e to the negative T over RC, like that. Okay, and they use delta V0, delta VC. That's fine. That doesn't really matter too much. The experiment is performed using a resistor R of 150 kilo ohms. Data for the potential difference across the capacitor as a function of time is recorded as this. So ln of this and this is below. Draw the best fit line for the data. So I'm going to draw a line. I'm going to make some adjustments to try to make it fit. Oh, that's not bad. That's pretty good. We'll leave it at that. Close enough. So we have this point here, and we'll pick this point over here, right? Let's calculate the unknown capacitance. So this is ln of delta Vc. So let's look at our equation right here, right? The equation that they gave us to use was this, right? And so we want to divide the two. Delta Vc over delta V0 equals e to the negative t over Rc, and then they do the ln of this guy of both sides. That equals ln of that, just negative t over Rc. So you could think of this negative 1 over Rc times t, right? So this is my x variable. This is my y variable. So this guy here is my slope. So my slope is negative 1 over Rc. So the slope here, I'm going to say that that's what? That's negative 0.8. What's the y value here? Negative 0.4. What's the x value? Is 0.6 minus 0.3. So that's negative 0.4 over 0.3. And what is that? 4/3? Negative 1.33? Yeah, negative 1.33. And that equals negative 1 over Rc. But R is 150 kilo ohm. So then the C is equal to, the negatives cancel. You just make it 1 over 150 kilo ohm times 1.33. That's about 5 microfarads, or 5 times 10 to the minus 6 farads. The capacitor is adjusted so the surface area of the plates is increased and the experiment is repeated. Would the slope of the best fit line of the second experiment be more steep, less steep? Well, the slope is negative 1 over Rc. And if you increase the surface area, so increasing A results in an increasing C, which results in negative 1 over Rc getting smaller, which means it's less steep. Right, so this is our slope value. The ideal battery is then replaced with a non-ideal battery with internal resistance R, and the experiment is repeated. With the slope of the graph of the final experiment change compared to the graph in part C? With the slope? No. Because the slope only depends on R and C. What would change is that the initial voltage that you would plot on the graph and stuff like that would be fine, and the numbers might be different, but the actual slope of the line is not going to change. Would the vertical intercept of the graph of the final experiment change compared to the graph? Well, the vertical intercept is when t is equal to 0. And if you look at our equation that we had, when t is equal to 0 would be natural log of, that would say the natural log of delta Vc over delta V0 equals 0, which means delta Vc over delta V0 would have to equal 1, which means delta Vc would equal delta V0. And the initial voltage would change, yes, because the initial voltage on the capacitor would be different. Oh, would the initial voltage on the capacitor? Let me look at the picture. Let me look at our circuit. We put an initial resistor right here in series. No, actually, sorry, I take that back. No, the initial voltage on the capacitor wouldn't change because, again, still no current would flow, so the voltage that the capacitor sees is still unchanged. So I would say no. The initial voltage on the capacitor would be the same. So like this value here would this would still be true. Okay. So okay. Last one. Light bulb resistance R is connected to a rectangular loop of wire of negligible resistance, a very long current carrying wire. The rectangular loop has a length of 4 centimeters, width of 2 centimeters, positions of one of the highest. So one of the longer sides of the loop is distance D, 1 centimeter above, parallel to the wire shown. The current in the long wire is flowing to the right. Okay, they have it here. Is given by, this is equal to C minus DT, where C equals 10 amps, D equals 2 amps. So that's 10 minus 2T. At time t equals 5 seconds, the current in the long wire is instantaneously zero as the current changes directions. Okay. What is the direction of any of the magnetic field produced by the induced current in the rectangular loop as the current in the wire changes directions? Okay, so right now, currently, if I have my right hand rule, right, my thumb is going to the right, and the magnetic field coming from this wire is coming out of the page. So if you're going to change the direction, that means the magnetic field is now going to go into the page. But the loop doesn't like change. It resists that change, so it produces its own magnetic field to compensate for the reduction or the change in the flux. That's the Lenz's law, right? It's going to compensate for that difference by creating its own magnetic field. And if its own magnetic field, what are they saying? It's what direction the magnetic field produces an induced current in the rectangular loop. It will be out of the page, okay? And your answer here is because the magnetic flux going through the loop is out of the page before the current changes. Before the current changes. So the reduction of that flux causes the loop to create a magnetic field to compensate. And that is Lenz's law. Okay, calculate the magnetic flux through the loop only to the long wire at time t equals 3 seconds. Okay, so the magnetic flux is the magnetic field times the area. However, the magnetic field varies, so we actually have to make this an integral because the magnetic field varies. What is the magnetic field varies is mu naught I over 2 pi r, right? You could derive that by Ampere's law if you want. So we have to integrate that. So we have to cut this. So how are we going to do this? Is we're gonna cut this thing up into little tiny rectangular slices and talk about the flux going through there. Well, the flux going through there is the magnetic field at that point, which is mu naught I over 2 pi r, times the area of this thing, which is 4 centimeters, or 0.04 times r. That's the area, times dr, because this thing has a thickness dr. And then we are going to integrate this from the distance of 1 centimeter all the way up to 3 centimeters, right? So 0.01 to 0.03. Okay. Now, the current at 3 seconds is 4 amps, right? Because at t equals, so I of 3 is equal to 10 minus 2 times 3, and that's equal to 4 amps. So then we're going to integrate from 0.01 to 0.03, 4 pi times 10 to the minus 7 times 4, divided by 2 pi r, 0.04 dr, and the integral of 1 over r is natural log. So it's going to be 4. So this will cancel to be 2. To be 2 times 10 to the minus 7 times 4 times 0.04 natural log of r from r equals 0.01 to 0.03. And then you can plug a lot of this into the calculator. Oops. Typed that in my calculator wrong. I have a sign. No, it's supposed to be ln. 2 pi e negative 7 times 4, 4.0 ln, yeah. And times, it's a really tiny number, which is pretty normal to be expected. So let's say it's 3.5 times 10 to the minus 8. What do they use? A Tesla meters squared or something like that? You could have done centimeters squared if you had just done it with centimeters, but I prefer to do everything in meters. Calculate the current through the light bulb at time t equals 3 seconds. So the current through the light bulb, okay, so the current through the light bulb is going to be V over R, but the V is the derivative of the flux, right? And so if I look at our expression, instead of putting in the 4, if I made this simply 2 times 10 to the minus 7, 10 minus 2t, 0.04, this is ln of 3, right? And then that's the flux. Then the derivative of the flux with respect to time is just 2 times 10 to the minus 7 times negative 2, 0.04 ln of 3. So I just do that calculation. It's a really tiny current. I just want to double check. Yeah. It's because it's a small area. And what can you do? It's a tiny area. Of course, it's going to be a small amount of flux. I'm getting a really tiny numbers. I get 1.76 times 10 to the negative 8 amps. And so what's the current? So that's the amps. That's the voltage. And so the current is the 1.76 times 10 to the minus 8 divided by the resistance. And the resistance is sorry, I'm having a little bit of trouble here. The distance, the resistance is 10 ohm. Okay, I was just checking over some numbers. I think it's right. A group of students attempts to experimentally identify whether the current through the light bulb is consistent with the current calculation for part C. The current in the rectangular loop is measured to be greater than the current calculated in part C. Which of the following could explain this discrepancy? Okay, so the current in the rectangular loop is measured to be greater. So what could be? The students did not account for the Earth's magnetic field. That wouldn't affect anything because the magnetic field presumably is not changing. The rectangular loop is tilted and not in the same plane as the wire. That would, if that wasn't in the same plane, if it was tilted, let me think about that. The magnetic field goes like this, and if your wire was like this instead of this, or like, tilted sideways, would that reduce it? Well, if anything, that would reduce the flux. Reduce the flux would reduce the current. So the current is this would reduce the current. Reducing the light bulb is greater than the recorded value. That would also reduce the current. The long side of the rectangular loop is shorter than the recorded value. That would reduce the flux, which would reduce the change in the flux, which would reduce the voltage, which would reduce the current. The current in the long wire changes faster rate than expected. That would increase the rate of change. That would increase the flux. Yeah, so this would increase the flux, the rate of change of the flux. Because the magnetic field is changing at a faster rate. Okay. So I think that is it on, got one more question. Later, same time, rectangular loop with a light bulb's rotates. The short side of the loop is 1 centimeter above the long carrying wire. The current in the wire is again initially flowing from left to right, given by that. The current through the light bulb in the new orientation is 3 seconds I2, which the following relates I2 to the current through I1. So here we're still having the same rate, right? But the flux ultimately, because you have more of the loop that's further away, you have less flux. And if you have less flux, then the induced current is going to be smaller. Okay, so that's me. So I would say you have less flux because more of the loop is further away. This reduces the induced voltage. And that results in a lower current, induced current. Okay, That one is a little bit harder for me. But yep, this thing, we're all done.